हाँ जी, अस्सलाम वालेकुम. Let us start. Bismillahir-Rahmanir-Rahim. This is the 12th lecture. Today we will discuss a new article. The article for today is called Bipolar Junction Transistors. And these slides have been prepared from our two textbooks. We can find the discussion on bipolar junction transistors in chapter number 3 of our first textbook and also from chapter number 4 in the second textbook. So these two textbooks that you see on the screen are the chapters that I have included in my slides. Right, now we come to the next slide. The next slide also shows the construction. It shows the number of PN junctions available in the PNP or NPN BJT transistor. There are two PN junctions. First is called the base emitter junction and second is called the base collector junction. Junction will be the place where our two different materials, they are combined. So if you look at the first diagram shows that of an NPN transistor. The first N type material and the first P type and the middle P type material have a base collector junction, and then the P type material and the second N type material, they have a base emitter junction. So the base collector junction and the base emitter junction, these are two junction these are two junctions available in both the PNP and NPN transistor. And if you look at the PNP case, here we have PNP transistor, the collector terminal, the base terminal, and the emitter terminal. The first P-type material combining with combining with the middle N-type material has the collector base junction, and the N-type material in the middle with the second P-type material has the base emitter junction. So the transistor has two junctions, has two PN junctions. Now we come to the next slide. In this slide, we will discuss the three regions of the BJT transistor. The three regions are as the emitter, the collector, and the base region. Now, the emitter region is called the emitter as it supplies majority charge carriers. The emitter is always connected in forward bias with respect to the base so that it supplies the majority charge carrier to the base. The emitter base junction injects a large number of majority charge carrier into the base because it is heavily doped and moderate in size. This is very important, and we will look at this statement that the emitter is heavily doped and moderate in size. So the function of the emitter is that it will always inject charge carriers. It will always inject majority charge carriers into the base. This is the purpose of the emitter. This is the working of the emitter. This is why we are using an emitter, that the emitter will emit or it will inject charge carriers into the base. Then the collector. The collector region is called a collector as it collects the majority portion of the majority charge carriers supplied by the emitter. The collector base junction is always in reverse bias mode. Its function is to remove the majority carriers from its junction with the base. The collector section of the transistor is moderately doped but larger in size so that it can collect most of the charge carriers supplied by the emitter. This is the function. This second paragraph defines the function of the collector. That is, the collector, it is called a collector because it collects majority or major portion of the majority charge carriers that are supplied by the emitter. The collector base junction, it is always reverse biased, and the function of this reverse biasing is to remove the majority carriers. The collector section of the transistor is moderately doped. That is, moderately doped means that it is neither heavily doped nor is it lightly doped. It is mediumly doped, but its physical size is always larger than that of the emitter or the base. And then third comes the base region. The base region, the middle region of the transistor, is known as the base. The base forms two circuits, the input circuit with the emitter and the output circuit with the collector. The base circuit is in forward bias and offered the low resistance to the circuit. The collector base junction is in reverse bias and it offers high resistance to the circuit. The base of the transistor is lightly doped and is very thin, due to which it offers majority carriers to the base. So the construction of the base region is that first it is lightly doped, and secondly it is thin in width. Okay, so now we come to the next slide. So this is the practical construction of the BJT transistor. We will see a comparison of doping and we will see a comparison of width. We see three terminals: the emitter, the base, and the collector terminal. The emitter is heavily doped and its physical size is medium as compared to the remaining two regions. Then the base is lightly doped and it has the most smallest width, whereas the collector, it is moderately doped and its physical size is the largest. So the doping comparison is that emitter doping is larger than the collector doping, which is larger than the base doping. So the base doping is the least, collector doping is moderate, and emitter doping is the maximum. Whereas if we compare the region, the width, the collector width is the largest, the emitter width is the medium or the moderate, and the least width in the transistor is that of the base. So this is the physical construction of the transistor, of the BJT transistor. So let us look at this comparison of doping. Let us look at this comparison of doping. The doping comparison is that emitter has the maximum doping, collector has the moderate doping, and the base has the least doping. The emitter, as the name suggests, emits carriers. It emits majority carriers. In case of an NPN transistor, those carriers will be electron. Doping concentration is maximum in emitter in a transistor. A higher doping level means more of these carriers will be generated per volume and time compared to a region with less doping. So higher the doping means that we create more charge carriers. The lower doping level decreases the conductivity, increases the resistance of this material by limiting the number of free carriers. The base has the least doping, therefore the base offers maximum resistance to the charge carriers. However, the collector has moderate doping. So if the emitter has maximum doping, the emitter will generate maximum majority carriers. These majority carriers will then be injected into the base, and then the collector will swipe away, or it will remove the charge carriers in the base collector junction, and the charge carriers will then be attracted towards the collector. Therefore we can connect, or therefore we can control the current flowing into, therefore we can control the charge carriers, or the majority charge carriers. We can control the charge carriers flowing into the collector. And then another line that we saw in the transistor construction was that the first line, the collector base junction is always reverse bias, and also The emitter over here, the emitter circuit is in forward bias. So the collector base junction is always reverse bias, whereas the emitter base junction is always forward bias. And this we will look at our slide number 13. Slide number 13 shows the normal operation of a transistor where the base emitter junction is forward bias and base collector junction is reverse bias. So to get normal operation from the transistor, we must always forward bias the base emitter junction, whereas we must always reverse bias the base collector junction. So let us look at the diagram. We see the transistor. This transistor is of NPN type. It is NPN transistor. The first N type material is the collector. The second N type material is the emitter, whereas the middle P type material is the base. If we want to forward bias the base emitter, the base is P type material and the emitter is N type material. So how can we forward bias base emitter? We can forward bias the base emitter if we connect the positive power supply, the positive of our external power supply to the base and negative of our external power supply to the emitter. Then we will forward bias the base emitter junction. So up till now we have satisfied the first condition. That is, we have forward biased the base emitter. We have forward biased the base emitter junction. Then the second condition is that base collector should be reverse biased. And how can we reverse bias the PN of the base and collector? We can reverse bias the base collector junction if we use V2, that is the second external power supply connected between collector and emitter. This second power supply should have a magnitude larger than the first external power supply. That is, V1 should be smaller than V2. When we connect the second power supply larger than the first power supply, then we reverse bias the base collector. How can we reverse bias? By connecting two power supply in the same direction. So let us see an example. Let us say that we are using V1 equal to, let us say, 1 volt, and we are using V2 equal to 2 volts. If emitter represents the ground, then base is at 1 volt and the collector is at 2 volts. The base emitter is forward bias because we only need zero point 0.7 volts to forward bias a PN junction. So our first condition is fulfilled. And now to fulfill the second condition, since collector is at 2 volt, what is the condition of base and collector? Are they forward biased or are they reverse biased? The voltage difference between collector and base is minus 1 volt. If we look from the base side and if we look from the collector side, then the voltage difference between collector and base is the voltage difference between collector and base is positive 1 volt, where collector is at 2 volt and base is at 1 volt. So the collector is at a higher voltage. The N-type material is at a higher voltage. Our N-type material of the collector is at 2 volts, whereas the P-type material of the base is at 1 volt. Therefore, the second PN junction, the PN junction between the base and collector, it is reverse biased. If we want to forward bias the base and collector, then we must reduce the voltage of the collector, but it will then violate our second condition. So to fulfill the second condition where the base collector is reverse bias, we are connecting collector terminal at a higher voltage. So this is how we will achieve both two conditions. Okay, students, I will finish this class over here and we will meet in a new lecture. Thank you very much.